sometimes we'll run into a function that looks like the ones that typically have limits that don't exist, but they actually do exist. For example, this piecewise function right here, g of x is equal to 3x plus 1 when x is less than or equal to 2, and 2x minus 9 when x is greater than 2. Anytime you have these piecewise functions, you plug it into both pieces and you check them. So when we plug in 2 into the left piece, we get negative 6 plus 1, that's negative 5. When we plug it into the right piece, 2 times 2 is 4, 4 minus 9 is negative 5. They give us the same value, so the limit of this function is negative 5. We are headed towards the same y value when we approach 2 from both sides. So we're good. Okay, when we approach 2 from both sides, the y values are negative 5, so the limit is equal to negative 5. Okay, let's look at B. We have a rational function here. We know that rational functions can have issues with poles. They can have issues with vertical asymptotes. What about when we plug in 1 here? Is there an issue? The top is not equal to 0. The bottom is not equal to 0, so it looks like we're okay. We get 5 over negative 15, that's negative 1/3. Okay, so just because you see a rational function, it does not mean that the limit does not exist. Okay, it does not mean that the limit does not exist. The limit won't exist if you're evaluating it at a vertical asymptote. If 1 were a vertical asymptote, the limit wouldn't exist. So tell me this, on B, where are some places where the limit may not exist? What are the vertical asymptotes for B? Can we factor the denominator? Thank you. X plus 4 times x minus 4. So, what happens? X plus 4 cancels, so what's going on there? That's a whole. X equals positive 4 is what? A vertical asymptote. So the limit will not exist at the vertical asymptote. Okay, the limit will not exist at the vertical asymptote. The limit may still exist at the whole. So let's look at why. Let's graph it. Okay, I know this is not what the question is asking, but I want to go down this trail anyways. All right, let's look at the graph. We see the vertical asymptote at positive 4. The left side is headed to negative infinity. The right side is headed to positive infinity. So at positive 4, the limit does not exist. At negative 4, though, over here, let's see here, negative 4 is right here. Now, it doesn't look like my graph is showing up. Let me adjust the window so I can kind of zoom in on what's happening here. I'm going to go negative 6 to negative 2 for my x's. Negative 2 to positive 2. Okay, so, I finally zoomed in enough. I can actually see that hole. I don't think I've ever done that on this calculator where you can actually see a little lip in the graph there where it's missing. Okay, but does the limit still exist here? Are we approaching the same y value from both sides? Yes. Yeah. We're undefined at that one specific point, but we are headed towards that one specific y value right there. We can look at our table and see, we can approximate. It's somewhere between negative 0.11 and negative 0.14. Somewhere in there is what the limit would be as we approach negative 4. Guess what? We can actually calculate that. What does our function simplify to? 1 over x minus 4. And we can plug in negative 4 now. Y'all remember finding the y value of the whole? You simplify it, plug in that x value, negative 1/8. Guess what? That's between negative 0.11 and negative 0.14. Okay, so none of that has anything to do with the limit as we approach 1. But I just wanted to talk about some of the other places where the limit may be affected because it's a rational function. Okay, so the limit exist at 1, it does not exist at 4, and it exists at -4. It's -1/8. All right. One more function here where it looks like the limit may not exist, but it truly does. Now, this is a different piecewise function. Okay, the ones that we've been doing up till this point have had the less than and the greater than. One side of the function looks like one graph. The other side of the function looks like a different graph. This is a little different. This says that we look like -x² plus x minus 11 as long as x is not equal to -2. That's another way of saying everywhere but at -2, we look like that parabola. And at -2, we're equal to +9. At -2, we're equal to +9. Here's the deal. If they're asking you about the limit as you approach that x value right there, which I'm asking you the limit as we approach -2, you plug it into the not equal to piece, which seems a little counterintuitive. But let's think about what this really looks like. Okay, this is somewhat of what the graph looks like. It's a downward facing parabola, y-intercept of -11. That's about all I know about it without just really getting into it. Okay, but at -2, we have this little bitty hole over here. Okay, at -2, the parabola doesn't apply, and the y value is way up here at +9. But here's what you got to focus on. The limit is asking where are our y values headed as we're getting closer and closer to x equals -2. So our y values are headed to this value here on the parabola. This random point up here doesn't matter. We are headed towards this y value down here. So when we've got these problems, we plug -2 into that not equal to piece. Okay, you plug it into the not equal to piece to evaluate that limit. So let's do that. We've got -2 squared plus -2 minus 11. You square the -2, get +4, but then there's a negative in front of it, so it ends up being -4 minus 13. So this limit is -17. Okay, that's the limit of this function as we approach -2. It's -17, but f of -2 is not. Okay, the limit as we approach -2 is -17, but f of -2 is not. You plug it into the equal to piece if you're just evaluating the piecewise function. Okay?